And then the equatorial I told you is parallel to the bond which is one bond away. So it's parallel to the bond which is one bond away. And again, all of this is, if you imagine a tetrahedral, you will be able to draw these nicely. Common mistakes that we see in answer paper is that people do draw it parallel, but they do draw it inside of something. Okay? They are like your equator, all the bonds are coming out. So don't make that mistake. So you draw it parallelly, but you draw the bond going inside the molecule. Geometrically, that is not possible. So remember, these are common mistakes in the exam. So ring flip, there were 8 people who had doubts on this. I'll again show this video.
Could you explain the thought was the same?
Question?
After difference 1 and difference 2, there was the same. Right? Could you explain that? In the previous slide, after difference 1 and difference 2, there was the same point, right? That same. After difference 1 and difference 2, there was the same.
So those above the plane remain above the plane. Unfortunately, I erased the drawings, but this edge is above the plane of the molecule. After flipping also, it is above the plane. It's not pointing down. Okay. Okay. Now back to the video. This is the planar form. I will pause it. So you see, in the planar form, there are 12 enriching interactions. The revision is taking a little bit time. I try to move through that. Now this is the chair form. Okay, this is your human projection which you do. Yes? Moving on. Now the ring flip will happen. This flap is moving up. I've already moved the little ahead. But you first get something called as a half chair. Then you continue, you get something called as a twist board. So this is twist board. Now the other side moves down. So the first flap moves up, now the other side moves down. Between them, you get the board form which is not tied. Now the other part will start moving down. Now as it moves down, you get the twist board first. Then there will be a part where it's all planar, which is the half chair, and then the ring form. Okay. So it's basically these rings, one flap moving down, the other flap moving up. That's essentially what the ring flip is. Okay. Those of you who understood this very well, we spend a lot of time over it. Now we move on to the post-butane interaction, which was what at least majority of the people had a doubt in this. I will quickly explain the principle behind post-butane. When you have ethane, this is the most favorable conformal for ethane. Nothing happens, it's almost zero in energy. Then I put one methyl. Again, no problem here. I put one more methyl. Now I generate 0.9. And also what happens is, this goes up from 1.3 to 4 kcals. That's because of steric interactions, both this way as well as this way. You have the CHs of the methyls in close proximity to each other. If you have a hydrogen, it's not a problem. But if you have two methyls, it does become a problem. So if I have, in that model, can you give back the Fischer projection? Who has it? Sorry, this class is going slow, but there were many doubts, so I wanted to ensure that it's clear. Once you are able to visualize this, everything else is very easy. So it's very important to get this concept right. So that's why I'm spending a little extra time. Those who understood, it's revision for them. Okay. So when I have two CH3s, what happens is, in the Gauss interaction, these two hydrogens come close to each other. When I have just a hydrogen here, that's not too bad. Okay? So this is your Gauss-butane interaction. Now if I have long roots here, it does not matter because the molecule can rotate. So it will not put the big group here. The molecule is smart, it will only put the hydrogen there. Okay? So that is the reason why you get Gauss-butane interaction in the first place. If I remove the methyl and put the hydrogen, there is nothing interacting. So they are not close to each other this place, this hydrogen and this methyl. Okay? That is the genesis of Gauss-butane interactions. Now in cyclic systems, what happens is that once you have a substituent, so once you have a methyl group, no, it can rotate, it can still rotate. Parts of the ring cannot rotate. But once you have a methyl group here, if I count the carbons 1, 2, 3, 4, I have exactly what I have in butane. Okay? This and this are 60 degrees to each other. The methyl here, okay? And if I count 1, 2, 3, 4, these two. Maybe from your view. See? Anyone else want to see this? And you can pass it along after that. So this methyl and this group, their dihedral angle is 60 degrees. You raise your hand. You can see it and then pass it on. Okay, so these two dihedral angle is now 60, where my finger is. Able to see it? If you are not able to see it, you can just count the carbons if that helps you. So this is 1, this is 1, 2 you cannot see, it's at the back. Okay. This is 3, this is 3, this is 4. Okay. This is 60 degrees. That's why it's called Gauss-butane. And because the molecule is now in a cyclic form and rigid, this is carbon, so it's like a CH2. So when I showed the butyl rotating, this case it cannot rotate, but the way its geometry is, one H is still close to that CH3, which is why you have Gauss-butane interactions. So there are two such Gauss-butane interactions. I can count here also 1, 2, 3, 4. Okay. So these two bonds and these two bonds, if I look at the dihedral angle, it will be 60 degrees. Okay. So that was a quick recap of Gauss-butane interactions. So two such in methyl cyclohexane. So now we are back on track. We had just started the 1-2. When you have two substituents, what happens? And you had done this activity where you had drawn this. So why is this called cis and why is this called trans? So those of you who did not understand that, I am repeating that as well. So in this case, these two groups, is this pointing up or down? This is pointing down, down, so they are the same. Cis. Here what is happening? So that's why trans. Here also same thing. So for trans, there are two possible conformers. For cis, there is only one, because even on the ring flips, one will be axial, one will be equilibrium. And the number of 1,3 diaxial interactions are 1, 2, 3, 4, the same as before. 1, 2, 3, 4. Again, same as before for methyl cyclohexane, 2. And then you have an additional 1 here, 3. Okay, so you have 3 Gauss-Lorentz interactions. Now the activity that you are supposed to do is calculate the number of Gauss-Lorentz interactions in the two transforms. So what are the number of Gauss-Lorentz interactions in the two transforms? Have you drawn it from last time? Quickly calculate the two Gauss-Lorentz interactions in the transform. Since we had already done in the last class, we have spent almost 25 minutes revising here. Yeah, correct. You hold on to this. There are 2 means 3.6 into 2. Yeah, but this is. Hold on. You're missing out some data. Anyone wants more models of cyclohexane? We have it here. You can pass it around. We are looking at Gauss interactions in these two conformers. And if I take the ring, how many of you put them? I don't know.